AdaCoder is a novel adaptive prompt compression framework for visual programmatic models, VPMs, that generates executable programs to answer questions through large language models, LLMs. The framework operates in two phases, a compression phase and an inference phase. In the compression phase, a set of compressed preprompts is generated, each depending on a specific question type, given a preprompt that describes all API definitions in the Python language with example snippets of code. In the inference phase, the framework adaptively selects a compressed prompt by classifying the question type and generates a Python program to answer the input question. The proposed framework addresses the limitation of VPMs, which require long input prompts to provide the LLM with sufficient API usage details to generate relevant code. AdaCoder employs a single frozen LLM and predefined prompts, negating the necessity of additional training and maintaining adaptability across different powerful black box LLMs such as GPT and Claude. The authors demonstrate the effectiveness of AdaCoder over the state-of-the-art ViperGPT model on 3 VQA datasets with GPT and Claude. The results show that the token length of input prompts is reduced by 71.1%. While maintaining or even improving question answering performance. AdaCoder outperforms LLM Lingua in the evaluations. The paper also reviews related work in visual question answering, including end-to-end models and visual programmatic models. It highlights the importance of interpretability and generalizability in VQA models and discusses the role of LLMs in code generation and reasoning. The authors also discuss prompt compression techniques, including fine-tuning, token reduction, and compression with small models. The proposed framework has significant implications for the development of more efficient and interpretable VQA models. By reducing the computational costs associated with long input prompts, AdaCoder enables the application of VPMs to a wider range of scenarios, including those that require real-time processing and low-latency responses. AdaCoder is a novel framework for adaptive prompt compression in programmatic visual question answering (VPMs). The framework consists of two phases, compression and inference. In the compression phase, a set of compressed prompts is generated using a large language model, LLM, with two instructions: rewriting API definitions and writing code snippets specialized for each question type. The compression phase is run only once to prepare compressed prompts. The inference phase adaptively selects a compressed preprompt to generate code for visual question answering. The phase consists of 4 steps: question classification, preprompt generation, code generation, and execution. In question classification, the input question is classified into a specific question type using a classification prompt. The preprompt generation step generates a compressed preprompt given the question type by aggregating the compressed API definitions, coding instruction, and code snippets for the question type. The code generation step generates a Python code using the compressed preprompt and input question. Finally, the predicted answer is obtained by executing the code using a Python execution engine. The AdaCoder formulation is defined by substituting the question classification and preprompt generation steps into the code generation step. The key novelty of AdaCoder lies in its ability to leverage the advantages of powerful black box LLMs without requiring comprehensive fine-tuning. The framework addresses the limitation of previous VPMs, which have long input token lengths resulting in large computational loads. By introducing an adaptive prompt compression method, AdaCoder reduces the input token length and computational load. The paper also provides a detailed formulation of the VPM process, including the code generation step and execution step. The code generation module is defined using a single frozen LLM, and the execution engine is a Python execution engine. The preprompt definition includes API definitions, coding instructions, and example code snippets. The paper also reviews the preprompt of ViperGPT, which is used in the experiments. Overall, AdaCoder provides a novel and efficient framework for programmatic visual question answering, enabling the generation of accurate and efficient code for answering visual questions. AdaCoder is a novel prompt compression method for programmatic visual question answering (VQA) that leverages the capabilities of black box language models, LLMs, to improve efficiency and reduce computational costs. The method is designed to compress prompts for VQA models, such as ViperGPT, by adaptively generating code snippets and API definitions based on the input question type. The compression process involves two stages. First, the input question is classified into one of 5 types: OBJ, CAT, ADDER, REL, and global, using a classification prompt. And then the corresponding code snippet and API definitions are generated using the LLM. The total token length of the compressed prompt is calculated as the sum of the lengths of the code snippet, API definitions, and classification prompt. The authors evaluate AdaCoder on 3 VQA datasets, GQA, VQA-v2, and NLVR2, and compare its performance with 2 baselines, ViperGPT and LLM Lingua. The results show that AdaCoder reduces the input token length by 71.1% while improving QA accuracy on all 3 datasets. The method is also shown to be more efficient than previous prompt compression methods, such as LLM Lingua, which cannot maintain the structure of code snippets after compression. The authors also conduct an ablation study to analyze the effect of question type classification on QA accuracy. The results show that using ground truth question types achieves the best performance, while using predicted question types or random question types results in a performance drop of less than 1.0 point. The study also highlights the importance of the instruction prompt for specializing code snippets to each question type. Additionally, the authors provide an analysis of the compressed prompts, showing that both API definitions and code snippets are significantly compressed. The compression is achieved by omitting unnecessary descriptions and condensing remaining sections into shorter sentences, leveraging the language understanding and summarization capabilities of black box LLMs. Overall, AdaCoder is a novel and effective prompt compression method for VQA that leverages the capabilities of black box LLMs to improve efficiency and reduce computational costs. The method has the potential to be applied to other natural language processing tasks that require code generation. The AdaCoder framework is designed for adaptive prompt compression in visual programmatic models. It efficiently generates programs for visual question answering by compressing and selecting prompts based on question types. The framework employs a single black box LLM for question type classification, textual compression, and code generation, eliminating the need for additional training. Experiments demonstrate the effectiveness and efficiency of AdaCoder compared to ViperGPT and LLM Lingua. The framework's performance is consistently high across various multimodal tasks, including visual grounding, counting, relative depth estimation, visual reasoning, image editing, and object tagging. Despite some minor errors, AdaCoder significantly reduces the frequency of wrong answers and coding errors. Future work includes defining fine-grained QA types and improving ILM's understanding of API usage. This research paper discusses the limitations and future directions of AdaCoder, a system for adaptive prompt compression in programmatic visual question answering. The authors acknowledge that their work relies on black box large language models, LLMs, which limits the analysis from a neural network architecture perspective. They suggest exploring alternative choices, such as open-source white box models like Code Llama and StarCoder, and combining white box and black box LLMs. The authors propose several future research directions to advance multimodal automated programming. These include developing methods for interactive code modification, automatic extension of APIs, and adaptively extracting necessary API definitions and coding examples. They believe that these advancements will be critical in automating large-scale multimodal software development, reducing computational costs, and saving energy. The paper also provides an extensive list of references, citing various works in the fields of visual question answering, language models, and multimodal learning. These references cover topics such as attention mechanisms, compositional visual reasoning, and prompt compression, highlighting the complexity and breadth of the research area. In terms of limitations, the authors recognize that their work is restricted to the traditional scope of visual question answering and that future research should focus on pushing beyond these boundaries. They also acknowledge the need for further exploration of white box and black box LLMs and their combinations. Overall, The paper presents a comprehensive overview of the current state of research in programmatic visual question answering and outlines potential avenues for future investigation.